I suppose, am I loud and clear to everyone here? Okay. So I'm probably the one that's standing between you and lunch now, so I'll try to make this as painless as possible. So good afternoon, everyone. My name is Venkatesh. I'm here on behalf of the Irish Center for High-End Computing. So just before heading into the content itself, ICHEC, we are the National Supercomputing Center in Ireland. And as a part of that, what we do is we operate the National Supercomputing Service in Ireland and work with academia, public sectors, and commercial organizations to work on HPC-related problems. And we work across a spectrum of application domains as well, environmental sciences, but it's not limited to that. So today, I'm here to present some of the work that our colleagues have been doing in applying HPC techniques to geophysics domains, particularly seismic dataset aided applications. So in the context of this presentation, geophysics applications, many of them deal with seismic datasets for different use cases. And primarily, one of the commonly used legacy data formats is the SegWi format. And people that might not be familiar with what that brings in terms of performance and parallelization is that the dataset itself is hosted in a non-contiguous fashion on disk. So primarily, you have your trace data that's segmented, and each of those segments is associated with a trace header. But then up front, you have a global header, so to say, that has the attributes for the entire dataset. So even though this may be stored contiguously in memory, the datasets themselves are fragmented pretty much across disk. And what's typically required is you would want, when you want to parallelize your operations, you would want segments, if not all of the entire dataset, to be contiguous in memory. That's the challenge. And just elaborating a little more on that, if you're talking about parallel processes that operate across multiple segments or objects from this SegWi file format, then each process is probably going to look at disparately located segments of your data. And so the challenge is it brings in a lot of difficulties in terms of I/O access patterns and poor cache utilization, and challenges in terms of how parallel processes can efficiently bring in memory the segments that are required for their operations. And this kind of needs an approach. Either one of the approach that's commonly used is commercial products that offer parallelized I/O solutions. They have their own proprietary data formats into which you would want to transform the legacy SegWi format. That's fine, but in many cases, the legacy code that exists operates on SegWi format, in which case we kind of could take an orthogonal approach where it's a library-based solution in terms of how you address domain-specific optimization of identifying I/O patterns that are relevant to the use case that you're using, and then having libraries that address the parallelizability of the I/O access for these SegWi formats for those application domains. So that's kind of where we are headed in terms of the ExSeisDat project. So the project itself aims at building a library that automates, to a certain extent, the parallelization of access to the I/O of these SegWi files. But on top of that, builds automation of the workflow itself in terms of seismic dataset analysis by leveraging the parallelization, the automatic parallelization of access to the SegWi files. It's primarily implemented in C++, but it comes with the Python wrapper by now. And it takes advantage of both I/O hardware and software technologies from the likes of DDN in terms of the IME bus buffer technology. So just a quick overview of how the ExSeis library is organized. What you see here are the internal layers at the bottom that sits on top of the file system. So the internal layers primarily target, the data layer primarily leverages the MPI I/O to facilitate the reading and writing of contiguous data blocks in memory. So that works in the level of the data objects that are stored on the file system. That's the data layer. But then the object layer is intended to work at the level of the SegWi file format. So if you remember the structuring of a SegWi file, you have the trace headers and then the data objects themselves. So the object layer is intended to present the abstraction of operating on parallel I/O using MPI/IO on the SegWi file format. And on top of that, what we have are the publicly accessible APIs for building applications on top of the internal layers of ExSeisPIOL. So ExSeisPIOL stands for ExSeis Parallel I/O Library. So the ExSeisPIOL itself allows you, is defined to simplify and automate the parallelization of reading and writing the SegWi files from the abstraction of a file that's being accessed in, I don't know, Kirchhoff's migration application or such. So this operates at parallelizing the access to the file itself. And on top of that, we have the ExSeisFlow API, which is basically a set of routinely or commonly used operations in the context of workflow of oil and gas code sets and so on. So typically, it's sorting, binning, tracing, and so on. So such commonly used operations in the seismic data set analysis. The ExSeisFlow leverages the automation of the parallel I/O and implements workflows that you can leverage for your applications. So just a quick example of what ExSeisFlow can deliver. On the right, you have the original workflow, whereby if you had, say, a sequence of operations to perform, from tapering to sorting to filtering and transforming and so on, how traditionally you would implement them if you had to do it barely on the SegWi file format is you would have each of those operations defined by compute and communication operations that you implement with respect to this SegWi file. So that's what are the individual steps here. But what ExSeisFlow allows you to do is it leverages the different abstraction layers of the ExSeisPIOL and then implements these operations by leveraging the automated parallelization on top of them. So what the end user would end up probably implementing at an application level is using these operations to implement the workflow. And it's open source, so it's not exhaustive, so to say. The next thing is the ExSeisDat library itself is being implemented to take advantage of technologies such as the burst buffer technology. In this case, in this project, we worked with DDN's IME. And we have, I'll finish off with some comparative results on how we compared the performance on just a lustre implementation of workflow that's implemented with ExSeisDat, but also compare it against when we have lustre working with the IME technology. So the use case that we present is a benchmark that we have in the ExSeisDat library, which works primarily with sorting-based operations. But when we tested it further on production-level applications that implement, say, for example, Kirchhoff's migration, the performances are relatively reflective of what we see here. So just looking at the hardware speed up in terms of how the read-write performs when we use just the lustre file system, and compare it with the lustre plus IME. What we see is that with respect to the red line on the top, the speed up that we get from IME is pretty much constant and scales as the size of the file itself increases. So in terms of write, we see good scale up in terms of how it performs for larger file sizes. In this particular case, roughly the I/O part of the code is around 45–50% of the entire code. So the rest of it is computation, whereas 48% of the code caters to the I/O. And what we are doing is we are not interleaving. So for this benchmark, we don't overlap I/O and computation, just to present a few more figures of where the time is spent in terms of I/O and computation. In terms of the throughput with respect to read-write, the throughput that we are referring here is how quickly we can have data pass between the file system itself and the parallel program. And what we see is, as expected, if I'm not wrong, the dotted lines are OK. So the blue lines are for just the lustre, and the red lines are for lustre plus IME. So as expected, what you would see is the IME adds a significant throughput increase in terms of both read and write operations. And just diving a bit more deeper, what we see is So this graph here basically is presenting the ratio of the different segments of your application in terms of the read, write, and compute operations. And the blue ones are basically the Lustre-based implementations, whereas the red scheme addresses the IME ones. What we see is, in the blue scheme, we are predominantly at an IO-bound computation region. So the light blue here is, except the light blue, the remaining blues are basically the read and write. And we are in an IO-bound application run there. And as we migrate to IME, what we see is we move away from the IO boundedness to more a compute bounded application execution. And that's pretty evident here because what we see is the remarkable speed up improvements that are delivered by IME is basically in the write operation, and that contributes to roughly, the read and write with IO contributes to roughly around 45–50%. So the overall runtime migrates from an IO bound to a compute bound execution. So we'll be happy to discuss any interest in the performance of IME in the context of these applications, or even how we can work together on seeing ExSeisDat, the library. It's in production, so I think I had it in the first slide, but here as well. So the partners that are involved are naturally DDN work with us to leverage their IME, but the production code for oil and gas is with Tullow Oil, so it's in production, the library itself. So Porrick Okonboy is our in-house performance engineer that leads this work. So we'll be happy to discuss either of this work. Yeah, thank you.